Hello, this is the demonstration of the sugar water demo. It's a polarized, it's a demonstration about polarized light types. So starting just to make sure for those of you doing the demo, you want to make sure that you have this code that I have up here on the screen. You want to set it up the sugar water so that it's firmly clamped with these three clamps all holding it. This is a little heavy because of the light corn syrup that's in here for your sugar water solution. It's a big too. This polarizer is glued to the bottom of it, so you won't have to worry about that. We'll take one of these lights from the demo room. You want to make sure it's close enough to the bottom and also that it is fully aligned directly in the middle of this. You can do that, as you can see, kind of by lining up this rod right against the edge of this polarized piece, and that should set up everything right. This piece of code, you're going to want to start with this linear one, especially for the breach type demo, and that's what I'm going to start with. And then we'll go into the physics demo for the full classroom demo for like undergraduate students later. Starting with the outreach demo. Hey guys, this is a demo about light. For the purposes of this demo, you may have heard, light's a wave, light's a particle. Don't worry about all that. For the purposes of this, light is a wave. Okay. Specifically, light is an electromagnetic wave. Now, you may have seen this fancy graphic behind me here, this nice little animation. This is showing light as an electromagnetic wave. You can see that blue line there. That's the electric part of it. The green line is the magnetic part of it. And combine their superposition, which is basically just combining the x and z parts of that wave, or technically y and z parts of that wave. The superposition is what you consider to be the actual light wave that you see. That's going to be that red. That's what you do by combining the magnetic and electric. So that's what I mean when I say light is a wave. This is important for this because, as you can see here, I have this giant beaker. This is actually full of sugar water. And so because light is a wave, when it's going through the air and like our line, it can be oriented any different way. It can be rotated any way. But if you use this thing called a polarizer, I don't know if any of you have polarized sunglasses, but if you use this thing called a polarizer, what this does is it makes sure that all the light is going through it the same way. So all the light for this one, we're going to say it's going up and down for this polarizer. Okay, we have this other polarizer. And if you line them up, if they're going the same way, all the light gets through perfectly fine because it's all going up and down. Now, if I take this and I rotate it, now all the light for this one is going to be going side to side. Okay, well, this one wants them up and down. This one wants them side to side. If you put them together like this, you'll see no light gets through. Now, why is that? Because, again, this one wants them up and down. This one wants it side to side. Only up and down is coming through this part. And so when you put this one that wants them all side to side, there's no side-to-side light getting through to this second one. That's why all the light cancels out. Okay? Now, my, great beaker contraption here. This bottom piece is a polarized lens, just like this. Just like this that I showed you, but a little bit bigger. This top piece is another polarized lens, right? So I can put them like this, look through, change them, and then the light will get through. There's no any light actually coming through right now, but if there was, light would get it. Okay? However, something strange happens, when I put the beaker in this. That's why we have the beaker. So I'm going to turn on this light. And, there's light coming through the beaker. It's going to shine directly through and connect this on top. If it's, parallel, exactly what expects happens, the light gets through. But as I put it perpendicular, actually, there's still light. As I actually rotate it, get all these different colors. I'm going to show you kind of what this looks like. I'm going to briefly turn off the lights in the room. Okay, and I'm going to actually probably turn off the projector for just a second. Okay, and so for the demonstration, I would simply hold it up here. You'll be able to see it for the camera. I'm going to put this in front of the camera so that you can see it better. You can see as I put it in front, the whole solution has this rainbow tinge. And this is what I'm seeing when I bring it up. And at the end of the demo, if anybody wants to come down, I can show you that effect. But in fact, it's exactly what I'm seeing. I'll turn these lights back on. Turn this projector back on for thinking. So that's what I'm seeing. Now the question is, why is the light able to get through this sugar? I just told you, you just saw for yourself that when the two are perpendicular, there's no light getting through. Not going to get through. But when I have these two perpendicular, the sugar in between, there's light getting. Well, obviously something's happening, right? So as we discussed, light is a wave. It has these two forms. Okay, it has this electric and magnetic field. Now, there's a lot of graphs and things here that you can play around with later. But importantly, there's these waves are what's called a phase, and currently they are in phase. So that means they're exactly in lockstep, and they're exactly how you use them. Okay? What I can do here is I can adjust the phase of one of these. And as I do, you're going to see that superposition gets more and more gets circular. So, at zero, it's a line. But as you further increase the polarization, the phase of it, you get this very circular line. Which get this really good for you guys. This is that circular line. That's really interesting. What does that mean? What does that mean for polarizers? Well, that's the light. It's traveling through this sugar water solution. One of the parts of the light, either the electric or the magnetic field, is changing in that phase. And it's becoming circularly polarized. That's what it means to have circularly polarized light. And that circularly polarized light isn't quite the same as the linearly polarized light that's coming through this polarized. And so because of that, you get this circularly polarized light that comes through, and it's able to come through the rainbow effect solution that you see when you look through the top. And that's where it ends the outreach type demo. For the full physics classroom demo, we'll get for the full physics classroom demo. You would want to do everything that I just previously did for the outreach demo. You want to talk about light, how it's polarized, linear, circular polarization. But you're going to want to continue with a discussion on chirality. And to do that, this giant spring here. This spring is a nice prop. Anything circular, or anything like a screw or a spring will do. It just needs to be threaded the same way all the way up. So what you want to do is you're going to start here. So now that this the circularly polarized light, there's actually a little bit more to it. So to get there, I'm going to have to explain another concept to you. It's the concept of chirality or handedness. Okay, how handedness works in chirality is a perfect example is this spring. You see this spring, you see how it kind of rotates up. I would kind of call this direction this way. Okay, just roughly, it's twisting this way, if that makes sense to everybody. Okay, and as it's twisting up and up and up, this is the direction of the spring. Now, if I flip this over, is the direction the same or different? And then you would further, field answers, all that kind of stuff, and then explain. You can kind of trace your fingers around it, and as you see, as I trace my fingers around this, it's the same direction. It's still going this way. That means even though I reflected this, no matter which way I reflect it, the direction is still the same. It's a concept in physics called chirality, or handedness. Basically, saying that no matter what reflection I do to this spring, it's going to be the same. It's going to kind of rotate in that same direction. This is kind of what's happening in our sugar water solution. So I have another graph for you guys here of a circular polarized light. Now, what I want to point out with this graph here is we have two different circularly polarized lights. One is clockwise, and another is counterclockwise. Okay, you can kind of see that here. I'll get it full screen for you guys. One is clockwise, and one is counterclockwise. Okay. And now the superposition of these two, what do you think it's going to look like? The combination of counterclockwise and clockwise polarized light. Field questions. Then you can show the answer. The answer is this yellow line. And as you see, it's linear. The superposition of two circular polarized lights going in opposite directions is linear. Linear polarized. And that's really interesting because that means you can also think of linear polarized light. It's two different circular polarized light waves. So if we think of our light coming through here, we can think of it as this linear polarized light. Each has two components, one clockwise and one counterclockwise. And as it's coming through the sugar water solution, what's happening is one of the components is getting put out of phase, just like I talked about in previously with that magnetic field causing that circular polarization. And as you put more and more out of phase, you can see here our linear polarized light is actually rotating. So what's happening truly is these chiral sugar particles, which have a handedness, are taking one part, either the clockwise or the counterclockwise, and the measurements, let's say, they're all going with the particles, so they all go through just fine. But the counterclockwise ones, they're getting just enough at every particle. And because no matter how you reflect them, they're all the same orientation. It results in a net, like face, between the two parts of the linear polarized wave, which is going to rotate that linear wave, and is why you can see the light coming through the other polar end, because the light is now at a different angle. So some of that light is at the proper angle to get through your second polarized. And then the true and final explanation of why the light gets through the sugar water solution when you put it through. And that's the end of the explanation for the full demonstration.